Okay, so welcome to Math 150. This is lecture 30, integration of simple regions. So what I want to do today is I want to, talk about how do we actually compute double, triple, and higher integrals in practice. And so if the region is nice, if the region is rectangular, we can often just reduce it to multiple examples of one-dimensional integration. As the region becomes more and more complicated, it gets a little bit harder. It turns out it doesn't have to be a rectangle. It just has to be set up so that if I fix one variable, I then have nice bounds for the other, and those bounds could depend on the first fixed variable. Let's talk a little bit about regions. So what is the simplest, nicest shape you can think of that's not a rectangle? Circle. Okay, so let's do a circle. So here is a circle. And now if I put into polar coordinates, I'll draw the circle in blue. If I draw it in polar coordinates, it's going to look like a rectangle. And so if I want to integrate in polar coordinates, it's going to be very nice because my region is going to be nice. The difficulty then is if I give you like a little box here, dx by dy, what does that become over here? And I'm going to write dr and r d theta. And the reason I'm going to write r d theta, and we'll talk a lot more about this, is theta is not a length. R times d theta is a length. So how many radians is it to go all the way around a circle, the unit circle? It's how many radians to go all the way around a unit circle? 2 pi. What is the perimeter of a unit circle? 2 pi. And if it's a unit circle, it's 2 pi. And so by using radians, if I go a quarter of the way around a circle, then the length of that arc is 1/4 times 2 pi. If I go 1/8 of the way around a circle, the length is 1/8 times 2 pi. So the way I get from an angle to a length is I multiply by the radius. If instead of using a unit circle, if I look at a circle of radius 10, the perimeter would be 2 pi times 10. And now if I go a quarter of the way around, it would be 1/4 times 2 pi 10. So this suggests that when we're trying to figure out how does the dx dy transform into polar coordinates, it might be related to dr and r d theta. D theta is not going to be a length. If I'm talking about areas, I should have meters squared, something like that. Dx times dy, that's meters times meters. That's good. Dr times d theta, that's not meters times meters. Dr is in meters, but d theta is not. However, r d theta is in meters. All right, this is going to be really big later on when we start getting to the change of variables. Right now, we're going to try to do something simpler. We're going to try to do over circular regions in Cartesian coordinates. You should not be doing this. The circle is screaming at you to change to polar coordinates. But let's try to do it. So let's say I give you a circle of radius r. So we have x squared plus y squared equals r squared. So I want to integrate a function. Do you want to integrate with respect to x first or with respect to y first? X. So x, if I'm doing the unit circle, where does x go from where to where? What's the smallest value of x? What's the largest value of x? Negative r to r. And then if I fix a value of x, so say I fix this value of x, oops, didn't change color. If I fix this value of x, I then want to see what is the range of y. So what's the smallest y it could be? What's the largest y could be? Well, if it was negative r, then I would be integrating over a square. I'd be going all the way down. So this lives inside a square. But you can see for a fixed value of x, I don't go all the way down to the bottom. I stop a little bit. We know x squared plus y squared equals r squared. So from this, we get y is plus or minus the square root of r squared minus x squared. So this would tell us if you fix the value of x, the smallest y could be is negative square root of r squared minus x squared. And the largest it could be is r squared minus x squared. And then I would just put in my function f of xy. Then is it dy or is it dx, which comes next? Dy, because we're doing the integral with respect to y first. And then dx. And so that would be how I would integrate a function in Cartesian coordinates over a circle. These bounds should scare you a little bit because they involve square roots. So if I give you a function that is very nice, then maybe the square root won't be so bad. Can anybody think of a nice function that you might want to integrate over a circle? There are two really good choices to make. So any thoughts about good choices for f? Or interesting choices? So one of them is f of xy equals, any thoughts? Okay, good. So what would you choose? What value for that horizontal plane? 1. And if you integrate f of xy equals 1 over the unit circle, it's going to essentially give you the area of the unit circle times 1. So this is essentially going to give you the area of the unit circle. So we can now try to use this to find the area of a unit circle. This will lead to trigonometric substitution, and then you always have to wonder, have we ever used the area of the circle is pi in doing anything with our trig functions? Yes.
So when we're integrating vertically, is it going to the end of the circle?
Yes.
So I'm just a little confused on why it's not r.
Well, because if it was r, we would be going all the way down to the bottom.
The bottom of the circle?
No, to the bottom of the gold square. Right, but only when x equals 0. We fix the value of x. Imagine you take x equals root 3 over 2. So y doesn't go all the way down to the bottom.
So r squared minus x squared, the square root of r squared minus x squared account for every single point.
Right, you give me an x and this tells you what's the largest y. If y went from negative r to r, then x squared plus y squared could be r squared plus r squared is 2r squared. You'd be outside the circle.
So if you went horizontal from a little bit higher, talking about dx, if you did r from a little bit higher, then when we go outside the circle.
Yeah, let me draw things. Just zoom in. So here is our square. Okay. So this is here's r. Oops. Here's r and r over here. Now I'm going to draw the circle. Okay. And I have the equation x squared plus y squared equals r squared. So you give me a value of x. And in general, there will be two values of y that work to be on the unit circle. So let's say I choose a value of x all the way over here. And I want to see what values of y can I choose and still be in the circle. What's the smallest value? What's the largest value? This is what we're calling a simple region, where we enter the region, we stay in the region, and then we leave the region and we never come back. So what are my ranges for y? Well, I get y is equal to plus or minus the square root of r squared minus x squared. If you had y go all the way down to minus r and plus r, that'd be all the way down to here. And all the way up to here. These points over here are not in the unit circle. These are outside.
q minus r plus r for x.
X, I agree with you that X is going from minus R to R. So once you choose a value of X, then you ask, based on that choice of X, what are the ranges of Y?
Okay, so it's based on x.
It's based on X. And that's why when you look at it, we're doing the X integration first. X goes from minus R to R. And then once we've chosen an X, then the bounds depend on X. This is why rectangles are so much nicer, because then the bounds are independent of X. Once you choose an X, Y is always going from C to D. Here, depending on what you choose, you're going to get different ranges for Y. Yep. There's one other choice. Does anybody know another choice that would be good for f of x, y? Yes. This just gives you the area of the circle. Because if I just integrate 1 over any set, that just gives you its area. So that's one good choice. Another good choice, yeah. Yeah, so what would you choose? Other good choice is f of xy is the square root of 1 minus x squared minus y squared. It's going to give you a hemisphere. So if you want to try to find the volume of a sphere is x squared plus y squared plus z squared equals 1. So if I choose the square root of 1 minus x squared minus y squared, if I could somehow integrate that, I would get the volume of a hemisphere. Okay, then double by 2 and I get the volume of a sphere. The problem is I would have to do these integrals in Cartesian coordinates. And so I'll leave that for you to try to see, can you do these integrals? And if you're doing these integrals, are you subtly using anywhere the fact that you know that the area of a circle of radius r is pi r squared? If you are, you're not really finding the area of a circle. You're basically using the fact that the area of a circle is pi r squared to then do even more work and then get back to the area of a circle as pi r squared. So, if you're using trig functions, in all of our analysis of trig functions, what are we assuming? But this is how you would do it. More generally, and I think this is going to answer your question now. Imagine some region, and let's say it's nice like this. Oops. Okay, so here what I'm going to do is I'm going to fix the value of x, and then I'm going to get my ranges for y. So y is a function of x. So on the bottom, maybe I'll write this as, y1 of x, and on the top, I'll write it as y2 of x. Or I might write this maybe as u of x for the upper bound, and I might write this as, or L of x for the lower bound. And now I can set up my integration. So let's say x goes from a to b. So my integral would be x goes from a to b. And now once I fix x, what's the range for y? What's the smallest value of y? What's the largest value of y? So do you want to try it? So looking at this picture, if I fix a value of x, give me the smallest value that y takes on for that value of x.
That point where you started, does it have a specific coordinate?
Well, I'm giving you equations of the blue line and the red line. I'm saying the blue line is y1 of x or L of x, and the red line is y2 of x or u of x. So what do you think the smallest value of y would be for a given value of x?
Y2 minus y.
No, y2 minus y1 is the difference in y. What's the smallest value of y? What's the coordinate of y for the smallest value of y for that given value of x?
y1 of x.
So it's just y1 of x. It's just y1 of x. That's the smallest value. What would be the largest value? Would be y2 of x. And so those would be my bounds. And so then I would just write whatever my function is. F of xy dy dx. And that's how I would do the integral. I would now have what this is called as iterated integrals. I just do them one at a time. So I first fix my value of x, and then I find where does y start, where does y end? Now, the question is whether or not I can actually do these integrals. The hope is that I can. The hope is that when I do the y integration, I'm going to get something nice, so nice that I can even then do the x integration. We could also try to do it. It looks like this region might also be, let's just do a new region just to be safe. So let's say I give you a region like this. Does everyone agree that this is a simple region as well? And now what I'm going to do is I'm going to fix a value of y, and it's going to be x that's going to change. So over here, I'll have x1 of y, or maybe the lower bound as a function of y. And here I'll have x2 of y, or my upper bound. Well, actually, instead of using L for lower and U for upper, let's use maybe, oh, this would have been okay. Let's use L and R of y. What do you think L and R stand for? Left and right. So again, notation that you can just look at and see. So this would be, the right side. This would be the left side. And so now we set it up so it's going to be y goes from, and now we have to choose, see, let's say the lowest value is C, the largest value is D. So y goes from C to D. And now we have to do the x integration. So what's the smallest value of x? It's just going to be L of y. And what's the largest value? R of y. And then we would just have a f of xy. Now it would be dx dy. And that's how you find the bounds of integration. You have to know what the functions are. So for example, let's say I give you two functions. So the blue is going to be y equals x squared, and the red is going to be y equals x cubed. And I'm going to plot, they intersect at 0. Where else do these two curves intersect? At 1. Now beyond 1, they flip as to which one is small and which one is larger. When x is big, I'd rather have x cubed than x squared. But when x is small, 1/2 squared is 1/4, 1/2 cubed is 1/8. So if I want to integrate this, what I could do is I could first fix a value of x. So I could integrate x goes from 0 to 1, y goes from, the largest will be x cubed, the smallest will be x squared, and we'll have f of xy dy dx. So that's doing things by fixing x. But yes. Oh, I'm sorry. I wrote it the wrong way. Sorry. Thank you. I wrote it the wrong way. Actually, I just have to erase the exponents. Oh no, no, because I'm using different colors. It's because I was intuitively looking at it as the cube is larger, and here the cube is actually smaller. So we should be going from x cubed to x squared.
Because the first one is from 0 to 1. Right?
It's from 0 to 1. If I was going from 1 to something else, like 1 to 2, then they would flip. So for this one, I'm integrating with respect to x first, nope, with respect to y first, with x fixed. And then once I do this, then I integrate with respect to x. Yes.
Where's the fixed point of x come in? Like the green x you drew on the arrow you drew on the diagram.
Right, it's just I'm letting x go from 0 to 1. For each value of x, I see where do I enter the region, where do I leave the region. So if x equals 0, the y should go from 0 to 0. If x equals 1, y should also go from just 1 to 1. If x equals a half, I would go from 1/8 to 1/4. So you give me a value of x, and I figure out what's the range of y. So as long as I know these curves, I can figure out what the ranges are. But we could, yes.
If you were integrating this from 0 to say 2, would you do it separately?
Yes, and so what you often do is you often split your region into a lot of nice regions. And so rather than trying to do one problem where you do everything at once, you say, well, look, if I'm integrating from 0 to 2, they're going to flip which one is on top after 1. So let me break it up. I'm going to integrate from 0 to 1, use one set of definitions, and then use another set of definitions from 1 to 2. So here I'm integrating with respect to y first. What else could I have done? Instead of doing y first, what could I have done? I could have done x first. So the value of y. And if I fix the value of y, I can now look and see what is the range of x. So I have to write my functions as functions of y, not as functions of x. So if y equals x squared, how would I write this? Not y as a function of x, but x as a function of y. Yeah, so this would also be, or x equals the square root of y. And the other one would be, or x equals the cube root of y. So if I wanted to integrate the other y, it would be the integral y goes from 0 to 1. And now for x, what's the smallest x can be? Square root of y. And what's the oh, sorry, so we've switched which color? Okay. And what's the largest x can be? Cube root of y.
I have a question.
Yes.
I know I said the answer, but I'm confused on why I said it.
So if you look at it, where do we enter? We enter on the blue curve, which is y equals the square root of x.
Oh,
So the smallest value x will take for a given value of y is the square root.
so it's starting at that y point.
So I fix my value of y and I keep walking until I enter the region. And I first enter the region at the square root of y. And then when I'm in the region, how long do I stay in the region? I stay in the region until I enter the region at square root of y, and I stay in the region until I get to the cube root of y.
That fixed point, are you starting at that fixed point?
Which fixed point? The y? So I have to do every y from 0 to 1. So the first is when y equals 0, then I'm going to go from 0 to 0. When y equals 1, I'm going to go from 1 to 1. And if I write down a generic y, so I'm using y as a placeholder, you give me some y between 0 and 1. What's my range going to be? And then I just keep changing the values of y. And so what we really have is we have a double sum just like before. Yes. Well, we just have to now put in a function f of x, y. And then depending on what function you put in, you then do the x integral, and hopefully that will work out. And then you do the y integral, and then hopefully that will work out. So it's now just 2 Calc 1 problems. The multivariable calculus is only in choosing the bounds of integration. Okay. So I'm going to do an easier region for a specific example. So let's do let's take the curve, y equals x from 0 to 1. And let's take my function f of x, y to be e to the negative y squared. Okay. And so here's, whoops. So here's my region. And maybe I'm a little confused because I've got a triangle here and I've got the vertical line. So it's a little bit easier for me to view this maybe as, let's fix y and integrate with respect to y. So here's 0, here's 1. If I give you a value of y, what's my left curve, what's my right curve? So if y equals x, what's my left curve for y, for x as a function of y? It's just y. And what's my right curve? 1. Those aren't so bad. So let me write down the integration. So y is going to go from 0 to 1, and then x is going to go from y to 1 of e to the negative y squared dx dy. Okay. So we have to integrate the function e to the negative y squared with respect to x. Can anybody tell me what function has derivative e to the negative y squared, or a function that has derivative e to the negative y squared as a function of x? Yeah, just x times that. So the first integral, I can just pull this outside of the integration, because that's a constant with respect to x. And then I'm going to multiply by 1 minus y dy.
What's the 1 minus y?
Well, I pull out the e to the minus y squared, and I'm just integrating the function 1 from y to 1. I'll put in a few more steps. Times x at y and 1 dy, right? Because the antiderivative is just x, and then I'm evaluating it at 1 and y, so then I'm going to get the integral y goes from 0 to 1, e to the negative y squared, 1 minus y dy, and now we're in trouble. I can integrate e to the minus y squared times y. That's set up for a beautiful u substitution, but there's no nice function that has derivative e to the negative y squared. We saw that in Wednesday's class. So unfortunately, if we try to do this integration, we're in trouble. Or at least we're in trouble if we do the integration this way. What if we try doing it the other way? What if we fix x? And now we try to find the lower bound and the upper bound. So can somebody tell me what would be the lower bound of this region? You give me a value of x, what would y be? What's the lower bound for y? 0. And what would the upper bound be? It would be x, because I've got the curve y equals x. So you give me a value of x, y is going to go from 0 to x. And so let's see if this gives us an easier integral to look at. So now I'm going to have x goes from 0 to 1, y goes from 0 to x, e to the negative y squared dy dx.
This is just like a small like, little thing. Are the brackets kind of redundant?
Yes, it's just to really drive home to you which one we're doing first. Can we evaluate this integral? Do we have a function that has derivative? No, we're in trouble. So unfortunately for this one, both ways, yielded something we just can't do. This is what life is like in general. I'm not going to lie to you and give you a function where it all works out and you change and everything works. No, this is the real world. Most of the time, you're going to be stuck like this. Now, every now and then, we will cook the books and we will give you problems on homeworks or exams where, yes, if you switch the orders of integration, one way will work out beautifully because everything has been carefully chosen. That's not how things are in general. This is what you do. You try both ways. You see, does either one work? Nope, neither one works. Now, I can give you a modification of this problem that is nice. So the modification of this problem that is nice is if instead, what if I gave you this region? So it's going to be very similar to what we had before, except I'm going to do it like this. So I want this triangle. And I'm going to still keep f of x, y to be e to the negative y squared. And so here's the line y equals x. And so I fix a value. Yes. So let me do the x integration first. So can somebody give me again, for this one, what would be the left bound as a function of y? It would just be 0. And can somebody give me the right bound as a function of y? Nope, almost. What's the right bound as a function of y? You can't give me x because x is not my variable. It's just y. I'm going from the red to the blue, and I want to write things as x as a function of y. So on the red, x as a function of y, it's just 0. On the right boundary, x as a function of y, it's just y. So I would have the integral y goes from 0 to 1. The integral x goes from 0 to y, and then my function e to the negative y squared dx dy. Okay. Now I've chosen this function to be very nice. When I integrate e to the negative y squared with respect to x, that's just e to the negative y squared. But now I get y minus 0. I'll do it slow. I get just x. I evaluated 0 and y dy. And it's not just the integral y goes from 0 to 1, e to the negative y squared y dy. Can that integral be done? Is there a function that has derivative e to the negative y squared y? Yeah, we could do a u substitution. So if we let u equal y squared, y goes from 0 to 1 becomes u goes from 0 to 1. Du is 2y dy, or y dy equals 1/2 du. So this is just the integral u goes from 0 to 1, e to the negative u times 1/2 du. So it's just 1/2 e to the negative u 0. I'm sorry. Why did I switch the order of integration? So this is trying to remember Calc 2 techniques. There's a negative sign when I'm integrating e to the minus u. So because there's the negative sign, one way people often do it is they just switch the order of integrations because that costs you a minus sign. If you're not comfortable doing that, then what you just have to remember is you have to have a negative when you integrate because it's an e to the minus u. And then the bounds would just be 0 and 1. And so it's just what function has derivative, 1/2 e to the negative u, negative 1/2 e to the minus u. Because when I take the derivative of that, the negatives will reinforce. Sure, there's two ways to handle this. One is to say, well, what function has derivative 1/2 e to the minus u? It's just negative 1/2 e to the minus u. Because when I take the derivative of this, I'll get negative 1/2 e to the minus u times the derivative of minus u. And the derivative of minus u gives me another negative sign. And so that's going to just give me a 1/2 e to the minus u. The other way, which some people, if you're really comfortable with your Calc 2, is they just say, well, look, I know I have an extra negative sign that I need to put there. If I switch the order of integration, that costs me a negative sign. So if you're comfortable, you can just switch the order of integration and not put in the negative sign. Either way is fine. This is now Calc 2, which you're all masters of because you've already done that class. So now we just plug in, and when we get 1, we would get minus 1/2 1 over e. So it's 1 over 2e. And when we put in 0, we would get 1/2. So this is the answer. What can you tell me about this number, 1/2 minus 1 over 2e? What kind of number is this? No. Very, very weak classification. What kind of number is it? It's not going to be an integer. It's not going to be a rational. It's not going to be anything like that. What other classifications of numbers do you have? Well, it's not quite. Nope, it's a real number. I don't care about the value. Just give me a rough comparison. So is this a negative number? Why do you think it's negative? It's 1/2 minus 1 over 2e. It's positive. So this is a positive number. So, it's not a number you've probably ever seen before, but we know it's positive. Let's think about what we're doing. The function e to the negative y squared. This function is always greater than 0. We're integrating a positive function over a positive region. What kind of number should we get? Positive. So as a quick check at the end of the day, oh, good, I've got a positive number. I hopefully have not dropped a minus sign. If I had dropped the minus sign over here when I was doing my integration, all of a sudden I would have had a negative number as my answer, and I would have known I made a mistake. I have to tell you, what am I integrating over? And so for this problem, I said, I want to integrate over this triangle. For the previous problem, I wanted to integrate over this triangle. And so by choosing my function and choosing my region appropriately, I can rig the problem so that one of the orders of double integrals is nice and one of the orders of the double integrals is nasty. Yes.
Is the only way we find out by testing?
Yep. By doing both of them. And again, there's only 2 possibilities, so it's not that bad. After a while, you start to get some intuition. This is, the baby is crying. Why is the baby crying? You start to be able to just look at it and see what you should try to do. But if you don't, there's only 2 possibilities. That's not an overwhelming number of things to try. If you go up to higher dimensions, you start to have more and more possibilities. But all the problems are like this. Find the lower, find the upper, or find the left, find the right. And depending on what I give you, it could be easier or harder to find those. Once you have them, you then reduce it to just doing some integrals. And so these are, yes.
So what's the difference between this triangle and the previous one? Is it just that you're taking?
So the difference is in the first, this was the triangle we had. And in the second, this was the triangle we had.
Is it that you're eliminating the x value so that it equals y?
I'm giving you two very different regions. And the reason I'm giving you two very different regions is I'm doing a cookbook problem where for this problem, one of them turns out to matter in terms of giving an example where if I switch orders of integration with the function I chose, everything works out nicely. We actually saw one of these before. When we were looking in the baseball problem, depending on how you wanted to look at it, we were trying to calculate what's the probability you score more runs than you allow. So I want to look at my region where x was greater than y. That's going to be this triangle. This triangle is all points where x is greater than y. So in probability, I might give you a function of two variables that tells you what's the probability I take on the pair x, y. And then if you integrate over this triangle, then that will give you the probability that x is greater than or equal to y. Or I might want to calculate what's the probability y is greater than or equal to x. And then I would have to give you this region. So the whole point about this problem is to show you first, if I give you a general function in a general region, we're not going to be able to integrate it. That's one of the points I want you to get out of this class. When you leave Calc 2, most professors leave you with the impression that you can do integration. I know there's at least one professor who tries to iterate numerous times to his students, you cannot integrate, I cannot integrate, none of us can integrate. Just most integrals don't have nice closed form solutions. Well, if we can't even integrate in one dimension, it's going to be worse than several. And then there's a whole slew of things you can do. Once we can figure out the boundaries, we can then integrate different functions. And so the question becomes, what are good functions to choose? So often, let z be some function of f(x,y), then the double integral over the region R in the xy plane of f of xy, dA is the volume under the surface z equals f of xy. So again, you can put in any function you want. It's which function is worth putting in. A good function to choose is if I give you some surface and I want to find what's the volume under the surface. Well, I now have some base. And so if I look at what's going on in the xy plane, and now I have some surface up above. And above each point here, what I can do is I can just get like a little patch over here and just come down like this. And that's going to, if I add all of those up, that will give me the volume under the surface. And so if things are very nice, I have a rectangular surface, a rectangular region down below, and I'm going straight up over a rectangle. Well, in general, we're not always going to be able to go straight up over a rectangle. I might give you, as we did in earlier, I might give you, say, x squared plus y squared equals r squared is in the bottom, and then maybe z is the square root of 1 minus x squared minus y squared. And this would give us a hemisphere. So I would have to find, how do I do this integral? This is not going to be a fun integral to do. You would have to be integrating, what function has derivative of 1 minus x squared minus y squared? There are tricks you can do if you know your trig substitutions. It's dangerous to assume people remember their trig substitutions. And of course, do any of these trig identities involve knowing that the area of a circle is pi? Okay. As an aside, you should have seen in some of your calculus classes volumes of revolution. So say here's x, here's y, here's some curve, say y equals f of x. And maybe what I want to do is I want to rotate this about the x-axis. And so what I'll do is, for each point over here, I'm going to just spin it around. They sometimes call it this like the shell method. And so what I can do is I can say, well, if I move forward a small amount dx, I'm going to get a small cylinder. And the radius is going to be f of x. So the volume, if we rotate about the x-axis, is going to be the integral. X goes from, say, a to b, then pi f of x squared dx. And we're basically just using the volume of a cylinder is pi r squared h. So I could treat this as a multivariable calculus problem, but I can also treat this as a one-dimensional problem. So just because you're learning multivariable calculus techniques doesn't mean you should use it for everything. So now, if you think about, what was going on when we were doing problems like this, there's not much multivariable calculus in this. It's very similar to Lagrange multipliers. In Lagrange multipliers, we take derivatives. We find the gradient of f, we find the gradient of g, and then we say grad f is equal to lambda grad g. The constraint g holds. We have now, if we're doing things in the plane, we have 3 equations, 3 unknowns, solve for x, y, and lambda. Although I'm actually happy if we don't solve for lambda, I just really care about x and y. Solving for lambda might help, but it's not essential. The amount of calculus we do, the amount of multivariable calculus we do is extremely small when we're doing Lagrange multipliers. We're just taking some derivatives and that's it. When you look at what's going on here, where's the multivariable calculus? Very little. The hardest part is finding the boundary equations. Well, the boundary equations, this is not really multivariable calculus. This is just going back to algebra. I give you some curves. If I give you y as a function of x, I might want x as a function of y, so I might have to invert things. So we saw that over here. So if I give you y equals x squared, it's not that hard to invert and say, oh, okay, you're giving me y as a function of x. I can give you x as a function of y. That's not a big deal. If I give you a more complicated region, it might become a lot harder. And then we plug those bounds in, and then we have to do the integration. And in general, the integration is not going to work out. And this is why, probably this is the only class I think where the first example they give you is an example that does not work. Because this is how it really is. Most of the time, it's not going to work. I did everything right. I wrote down my bounds of integration. I found my functions. I tried to do the integral. It didn't work. I then switched orders of integration. I found the bounds again. It didn't work. Yes?
So on the exam, you don't get them.
No. If you get something like this on the exam and it doesn't work, what does that mean? I'm sorry? Who is the you? Or me. One of us is making a mistake, right? Either you are doing a mistake when you're doing the problem, or I did a mistake and I did a slightly different integral and I dropped a factor or put in a factor and made the integration nice. But on an exam, I'm not going to give you something like this unless I say, integrate as much as possible. I could give you something, generic like that. Anything I give you, it's integrated. And if I give it to you, you should be able to do it and you should be able to get to a nice answer. And if you can't, you're either making a mistake or I'm making a mistake. And then just come up and say, Professor Miller, are you sure that, this is the function you want us to look at? Or that this is the region you want us to look at? Can you double check your work? Okay. And again, in the real world, you would just plug this into Mathematica or something like that. Place to stop.